All right. Hi everyone. Welcome to the Topos Colloquium. We took a break for a while in July and early August, and this is our first talk for the series for this half of the year. And I'm very pleased to have Schreiber today, and he's going to be talking about quantum programming via linear homotopy types. So whenever you're ready. Thank you so much.
Yes, thank you very much for the invitation, for the introduction. For the second invitation, right? So this is meant to be the second part of a talk that we tried some months back, which was interrupted by my vacation Wi-Fi not standing up. And back then, I think I didn't manage more than during 30 minutes going through the history of the idea of linear types. So I thought this time maybe I'll try another approach and do very little background in history and jump into some content. Let's see how this works out. So what I want to present is a project that we are working on at what's now called the Center for Quantum and Topological Systems at New York University in Abu Dhabi. This is a joint project with David Myers, who's in the audience, I see, and with Hisham Sati, who is the head PI of that center. So this is part of a bigger project. We're looking into quantum programming. I'm not assuming that you know anything about quantum programming, though I guess some of you might just as well. The talk that I'm going to give is actually content-wise an easy exercise in basic category theory, but motivated from this, I want to show some interesting, nice structures that exist on certain categories of index vector spaces, which easily motivate, I would hope, some deeper perspectives on the matter that are related to programming languages and stuff. But I will not assume any background on that. So let me maybe just jump right into the little bit of motivation that I would want to give. Let me make this window smaller here so that I see my own slides. So just as a minimum of motivation, just out of the blue, I'll show this diagram here, which indicates how people these days think about what a universal quantum computer should eventually do. So as you certainly have heard, and some of you may be working on this, there is much excitement these days about the idea that quantum computing with the physical principles of microscopic quantum processes is a real thing. But the actual quantum computers that currently exist, the so-called NISQ machines, are far from the universal machines in the sense of universal Turing machines that you would hope to be able to program in arbitrary ways and control with classical computers. The diagram that is shown here is meant to indicate what an actual real like heavy-duty quantum computer eventually should be structured like, where the actual quantum processor shown in this cartoon picture in the top right is just a small component, whereas a usual classical computer shown on the left keeps interacting continuously with this quantum machine, sending in information, reading out quantum measurement results, and based on these results, doing or instructing the machine to do whatever it is that a quantum machine does. What the diagram is meant, this somewhat silly diagram, is meant to highlight is that this is in general going to be a complicated process. And the point of this that I just want to make is that if you want to be sure that your quantum program works properly, you somehow have to think about theoretically about certifying or verifying such a complicated quantum classical interacting process. And that is the theoretical open problem that I think has remained fairly wide open. And this is the, if you come from the quantum computing perspective, this is what we, with this approach of linear homotopy types, think we can contribute to. There's other motivations for what we're doing here, but this is maybe one that is kind of generally accessible. Just to highlight here in this cartoon picture, which also I will not really spend much time with explaining, but just to highlight, this is what a standard quantum information textbook will show, quantum information theory textbook will show you right away as an example of a standard so-called quantum protocol, which is meant to indicate that on the left, we send in some quantum data, and then there's different things we want to do with it. The boxes, the ordinary boxes, these H's in it, indicate certain quantum operations that we want to do on them, which are mathematically or category theoretically, if you wish, really just linear operations on certain linear spaces of states. But then, and that is what relates to this classical quantum interaction that I mentioned with the previous diagram, then there is something called mid-circuit measurement results. And quantum measurement, as you certainly have heard, is a kind of, in its way, subtle process which makes this linear quantum information collapse, as one says, since the 1920s, now almost, or exactly 200 years ago, to a classical state. And then based on this classical outcome, we, like in this quantum teleportation protocol, we want to control further quantum processes on this quantum data. So, just saying this in words might seem it's not too hard to come to grips with this. But the thing is, when you try to actually formalize this, what is actually going on here? What is it that you actually need to do to write a programming language, preferably a certifiable one, a verifiable one, a typed one? What is it that you need to do to control all this? Well, first of all, you do need a classical programming language for the classical background. But then it has been long understood, and this is what I spent most of my time, all of my time, in the last talk with, you need to be finding some language to talk about the actual quantum processes, which, and this is the whole point, are crucially different from the classical processes in their linearity. So you want to have some what's called linear data types. But then the question is, now you have a classical language for the classical computer and this linearly typed quantum programming language maybe for these quantum gates, but how is it that they actually interact? And that question, even though it may superficially sound rather trivial, that was actually wide open. And the reason, or that is the reason why existing, so there, since a few years now, there has been wealth of activity, or a lot of activity on, quantum programming and writing quantum programming languages, but all of them, I'm speaking somewhat broadly here, but essentially all of them suffer from this problem that there has not been an actual quantum programming language in the universal sense that you could, write arbitrary quantum circuits in it with typing and everything. What has been there is classical type theories, of course, classical programming language backgrounds such as Haskell or Coq. And what people have been doing is implementing inside these classical programming languages, implementing the kind of extra bells and whistles that should be needed for quantum programming. But this means that the fundamental language that these embedded quantum languages are written in, the host language does not actually know about quantum principles. It cannot, for instance, check that something is actually a quantum gate in the sense that it's actually unitary or linear. Or it cannot at least check it natively. There's no actual type checking intrinsic, say, to Haskell of what it would mean to have a linear type. And the problem here ranges deep. It relates to the problem that in parts of category theory and type theory is known as the problem of bunched logic, where you say, okay, suppose we have Cartesian products and a non-Cartesian tensor product on our category of types. What does it actually mean now to put both of these, or types related by both of these products, into contexts on which we want to operate? And again, it may sound simple, but this has, turns out, lots of subtle issues that have, one can argue, never really been resolved. And the starting point of this project from this perspective is that we claim that recently, actually, it has been resolved. So this is this claim that there is now, at least on paper, a new novel type theory, programming scheme, which I'm referring to here as linear homotopy type theory, which does, for the first time in a sense, properly satisfactorily combine the classical and this linear part of type theory. So back in 2014, I wrote this node quantization by linear homotopy types, where just kind of without really much knowledge of full formal type theory, just went ahead and said, look, if we just look at the categorical semantics that was very well understood at that point of classical homotopy type theory, and if we know our homotopy theory, then I said there's kind of an obvious linear tweaking of this situation, which looks just like it ought to be following the same principles as ordinary type theories or homotopy type theories, except that some of the types are now linear. And then some years passed, and I didn't get much feedback on that article actually, but it so turns out that well, I don't know, last year or 2 years ago, Mitchell Riley, who's now thankfully a member also at New York University in Abu Dhabi in our research center, he, in his doctoral thesis, wrote down an actual formal type theory which calls a bunched homotopy type theory, that does implement these ideas of what I, for the sake of evocativeness, want to call linear homotopy type theory. And I invite you to, if you follow this webpage here, you'll find Mitchell's thesis. So a bunched homotopy theory, type theory of synthetic stable homotopy. Is that right? Maybe there's a typo here in my reference. Anyway, if you Google for these terms, you'll easily find his thesis and can see this full type theory. I'm not actually going to, because it would also take way too much time. I'm not going to formally introduce this. As I mentioned at the beginning, what I want to do is I want to show a very simple, almost, very elementary, almost trivial little category, an exercise in category theory, which interprets a small fragment of this linear homotopy type theory. And just by analyzing this category, we will see what the type theory is actually going to do with it. So our claim here is, which I'm just going to partially justify in this little talk here, is that using this linear extension of the classical homotopy type theory, we do finally have, this kind of the grand claim here, a paradigm, even though it's not implemented yet on an actual computer, but on paper, a paradigm that does solve all these previous technical subtleties and does allow us to reason in and write fully certified programming languages that encode not just the classical and not just the purely quantum part of quantum computation, but crucially this interaction. And since it's also homotopy-theoretic, as I've been mentioned, even though this is really a side issue for my talk today here, this actually also knows about what in quantum computing is known as the topological part of quantum computing, which is a huge deal for the idea of actually realizing quantum computation. And that's why in this diagram here you see that apart from this quantum system language that I'm actually going to try to indicate a bit, there's also this homotopy-theoretic aspect embedded into this linear homotopy type theory, which allows us to talk about this topological aspect of quantum computing. This is the content of another article that David, Myers, Hisham, and myself have just put on the archive just a few months earlier, which you can find, which goes into great detail of what homotopy type theory without the linear aspect has to say about this topological part of quantum computation. Today, I'm going to focus entirely on how some categories that mix linear and classical aspect, we see structures of a good universal quantum language emerge. So that's the plan. And here's just a little bit more technical before we look at the actual example. Let me show this very fond of this microscope here. Can you see this little magnifying glass? So the basic idea of how to go about this is, which is maybe not, I don't know if depends a bit on your background. This is something like a well-kept secret, which is not as widely advertised as it should be. So there is this way of coupling classical and quantum data by using a category where you parameterize all the linear data over the classical data, in the sense that is, I try to highlight in this cartoon here, where seen from far away, your entire category looks just like a classical category, meaning technically, for those who know these terms, we're actually going to be modeling or interpreting our language in an actual topos, or rather an infinity topos. But it so happens that actually all the objects in that sort of classical context and that classical theory, if you look closely in a way, and I'll make this precise in just a second, if you zoom in on them, if you magnify infinitesimally or microscopically, you actually see that all of these have a quantum halo. All of these classical looking types have a classical or infinitesimal halo around them. This word halo is actually quite good in this context because it's used in non-standard analysis for infinitesimal neighborhoods, and that is, in a technical sense, exactly what is going on here. What we're looking at is something that in 2013, I think I called a model of infinitesimal cohesion. There's, in a precise sense, and we'll see this in the diagram that is coming up here at the bottom of the screen now in more detail, there's in a precise sense an extra structure in linear homotopy type theory on the classical types, which exhibits every type as being an infinitesimal extension of a classical type. So here's how it works. The idea is rather simple, actually, in this broad brush kind of picture here. So in the spirit of so there's a, how should one say, there's a paradigm here where you want to add new structures to an existing programming language by kind of carving out, by keeping your original language and just saying, well, what if I add more axioms that make all the types already had seem richer than they previously were. So you don't just add analytically sort of new structure, but you say, well, let there be an operation which is such that if it does exist on objects, then the objects apparently must have had an extra structure. So this may sound mysterious, but here's already the illustration. So we're going to consider a category of classical types, if we wish, which is going to be an actual classical topos, an infinity topos. But inside that, we pick a subcategory, which I'm calling classical types. So these are the actual, purely, if you wish, classical types, even though also this turns out to be just a topos. This is the magic that's gonna, I'm gonna amplify this in a moment a bit more. And we ask that this category is embedded, and this embedding has both a left and a right adjoint. This is called a bireflective or ambidextrous or whatever embedding. And if you think about that, what this means, this is something that, or if you think of examples where this is true, this is a property that is shared, for instance, by categories of bundles, of vector bundles, of arbitrary base spaces, where the types here are these bundles, which you might think of, with the linear fibers as being little thickenings of their underlying classical base spaces. And the fact that this inclusion, given by sending a classical type to the zero bundle over it, has a left and a right adjoint, comes down, if you work it out, to the fact that the category of vector bundles, so fiber-wise, has a zero object, which is both initial and terminal. So in a way, this ambidextrous adjunction is a first modeling of the fact that the types in this bigger category of types are going to look like, if you wish, pointed, or sometimes people say retractive bundles over base spaces. So those that have something that behaves like zero sections. So from this, you see it's a first step towards linearity. This is the first ingredient that linear homotopy type theory adds to just classical homotopy type theory. It says, this is easier said than done, but yeah, we say we add a modality, we add an operator that behaves as if it were, or as if it behaves like the endomorphism, the monad comonad that is or would be induced by such a bireflective embedding. And here on the right, I'm indicating in more detail the actual categorical semantics of these things. So I don't want to dwell too much on homotopy theoretic aspects, but since I mentioned homotopy type theory, I should mention that there you should think of these classical types as actually being infinity groupoids. And if you think of them as being not just simplicial sets, but simplicial set enriched groupoids, simplicial groupoids, then this inclusion can be modeled by the inclusion of this base category of simplicial groupoids into the Grothendieck construction over simplicial groupoids of the simplicial categories of what's called simplicial local systems, if you wish, simplicial vector bundles over simplicial groupoids. Anyway, we're going to look at just the zero sector of this, by which I mean, I was just chatting about this with David the other day. So if we now say zero sector, actually we need to be a bit more sophisticated than we had to be in ordinary say homotopy type theory, where we just zero truncate. Since we're now mixing stable and unstable aspects, zero actually means zero truncated on the classical objects and means the heart of a T structure on the linear types. Anyway, so there's a well-defined notion of zero sector, and that's what I'm going to zoom in now and give you an idea of a simple but very, very illustrating example of what this does. So now I need to jump through my document here. I'm sorry that I'm not showing slides, but I've prepared very nice little diagrams in here. I think they will be just as good as slides. So after this introduction or motivation, now comes the elementary category theoretic part of my talk. And I do want to maybe suggest to think of many of the things that I'm going to say now. Well, I personally do think about them as a kind of Yoneda lemma-like principle. So the Yoneda lemma, as you know, stands out as being an almost triviality. It's elementary to the, it's an exercise to solve, to prove. It's not a deep, you don't win a Fields Medal proving the Yoneda lemma. And yet it is so very fundamental and just appears everywhere. And I think this is, so to some extent, not trying to oversell this here, but to some extent, what I'm trying to show is of this form. These are very elementary category theoretic considerations, but the point is I hope to be able to illustrate towards the end of the talk is that they're actually they point to very powerful general principles. Anyway, so here's our example, if you will. I'm going to consider the following super easy category. So I'll write classical types just to be suggestive, but by that I just mean in this, for the purpose of the remainder of this talk, of course, in general, it will be something more general, but for the remainder of this talk, it's just the category of sets. These are classical types that should certainly make sense. Morphisms are just maps of sets. This is just sets, I call them classical types. And now, keeping with this idea of attaching highbrow new terminology to ancient structures, I'm going to write quantum types for the category of complex vector spaces, which I write as C modules here, mod C. So these are complex vector spaces, modules over the complex numbers. And the morphisms now are just linear maps, just the category of complex vector spaces. And now we begin to couple these two things. This is all super elementary, and people in K-theory, for instance, study this kind of structure that I'm going to evoke now all the time. But anyway, let's just look at it. I'm going to say now, well, suppose I have a type here, a classical type, so a set W. I'm going to consider the category of something like W indexed, so W parameterized linear types. But this is just going, I'm just going to mean now vector bundles, if you wish, over that base classical type W. So these are just vector bundles over, in this case, discrete sets. But this can be generalized to vector bundles over general topological spaces, but that's, that gets us into homotopy-theoretic territory, and that's why I'm disregarding it for the purpose of this talk, just looking at this zero sector here, where we have just vector bundles over sets. And I'm going to write them. This turns out to be useful for, you'll see this in a moment, for analyzing these structures. I'm going to write these vector bundles as these calligraphic H's, which are supposed to remind you of Hilbert spaces, even though at this point, this would come later, but not today. They're just complex vector spaces. There's no Hermitian structure yet on them. We can do that, but disregarding it for the moment. And so this notation just says there's a vector bundle H, and the bullet just means it's just an indication of all its fibers. So for every element in W, we're going to have a fiber, which is just a vector space. So in this category, quantum types over W, the objects are all over W, they're all vector bundles over fixed W, and the morphisms of, if you wish, vector bundles over W, so they're just fiber-wise linear maps, phi bullet. So for each W, there's a member. And now comes the crucial step, which is trivial, but well, it becomes less trivial in the homotopy-theoretic context. Anyway, we can consider now the amalgamation of all these categories of W-indexed quantum types. Technically, this means we form the Grothendieck construction, indicated by this integral sign here as usual. So we say, okay, so for every classical type in here, we form this category. This behaves nicely. This is an indexed category. This pulls back and pushes forwards in all kinds of nice ways. So we can form the Grothendieck construction, which in concrete terms just means now we're considering the category. So type is not just my idiosyncratic new terminology for the category that you might just call, this doesn't have a standard name, which maybe indicates that there's a bit of a blind spot here. It's the category of vector bundles over arbitrary base spaces, meaning one object is a vector bundle shown here. It's fibers H over a base, which is just a set W. But there's now morphisms to vector bundles that may live over a different base space, W prime. And so such a morphism is a morphism of base spaces. And, there's now many ways you may want to think of this. And the linear map on the fibers that covers that base map, which is a fiber-wise linear map. So that is the category I'm going to call type. You see already, if you look back, that I'll come to this, but you can already, mentally see it very easily, that this category of type will contain the classical types as a full subcategory by assigning 0 fibers. This will be a bireflective embedding. So this is the very simple, basic example that runs our theory. So I have some remarks now here on how we want to think of these types. Maybe I'll skip over this. Here's the first little fact that is an exercise, but it's quite curious actually if you work this out. The claim now is that this category, it's not surprising, but it's still good to work it out. It's well, it's not surprising in broad brush strokes, but I think the formulas that appear now, I don't think many people have thought about these before. I don't know. They're not discussed in the text. But anyway, we can now do the following. So we have two monoidal structures floating around here that clearly want to be combined. On the one hand, of course, our classical types, the category of sets, is a Cartesian closed category with Cartesian product of sets as the monoidal product. just function sets is the hom. So I'm going to, gradually, as you can see already, I'm going to gradually shift to more type theoretic notation, even though I'm just doing category theory. So instead of writing my internal hom with angular brackets, or calling it maps or something, I'm already, writing it as an arrow. But I'm not doing that. This is just category. This is just my notation for the internal hom in the category of sets, maps from here to there. And then, of course, the category of what I call the purely quantum types, the category of vector spaces, has also a common monodal structure. The non-Cartesian one is the tensor product, the ordinary tensor product of vector bundles, and it is closed. It has a corresponding internal hom being just, I'm using this lollipop notation here as usual for linear internal homs. This now denoting the set of linear maps between these vector spaces, but equipped with its canonical vector space structure. So the vector space linear maps from H to H prime. And so these are monodal structures we have separately on our classical and quantum type categories. And now the claim is that this induces to, this makes a doubly, as some people say, a doubly closed monodal category. Let me see if I can put this on the screen, like so. This makes our category of types, remember which were these bundle types, doubly closed monodal in an interesting way. So first of all, the claim is, part of this proposition is that the category of types of linear bundle types is again Cartesian closed. Its Cartesian product is, unsurprisingly maybe, the one which reads into bundles on different base spaces, forms the Cartesian product of the base spaces, and forms what in the K-theory literature is known as the external direct sum or external Whitney sum or something. So it forms over the point that is labeled by little w and little w prime. It takes the fiber of H over W and of H prime over W prime. So my notation is meant to be, I don't know if this works for you, but it's meant to be self-explanatory. It just says, you need to plug in a W here and a W prime here. And if you do that, you have your fiber. So the fiber over W prime is HW prime. You see this direct sum, of course, is the Cartesian product on vector spaces. And so we're just sort of forming in both components the Cartesian product. Now here's the first interesting thing to work out. This is an interesting exercise. So the claim is, this product is maybe easy enough to understand and guess, but it turns out this is actually closed. This has actually an internal hom, which means there should now be a vector bundle of maps between any two of these bundles. If you work this out, it comes out as follows. It comes out, right? So I'm showing here's a bundle, here's a bundle. I'm describing now the internal hom, by this arrow. The internal hom bundle between them. It turns out its underlying set, the underlying set of such maps is what you would expect. So if you unwind this notation, it just says a point down here in this internal hom is a map of the base spaces. And so this classical notation, ignore it for a moment. This is just, I'll explain this in a second. Maybe this is not well organized here. So this just means we form the ordinary set. We form the ordinary set of linear maps. The thing is just previously I declared, or I didn't even. Anyway, so this is the set of linear maps between the fibers, right? So this piece down here is just a more syntactic notation for the homs. Let me just scroll up again. For the homs between our bundles that I showed before here. Oh, my computer stopped scrolling somehow. Right, so a map between these bundles was a map of base types covered by a map of linear types. And if we just unwind what this means in more syntactic language, sorry, something is getting in the way here. Anyway, so it means this. But now the interesting thing is, this is just the base space of this bundle. So we're forming an internal hom in a category of bundles. We are actually getting a bundle of homs. And if you work it out, you find that the fibers here are actually products of just the second guy here over, over the corresponding, it depends on this map here. And you kind of taking the product, all the fibers and the images of these maps. That's just how it comes out. We'll see this in an example when it will become more clear. But you see at this point, maybe, because I don't think this is something you would just easily guess. If you hadn't thought about it before, you don't go to the board and say, oh yeah, that's what it is. This is something, and this points to something interesting going on. And we'll see more of this in just a second. Namely, we see something similar happen with the other internal homs. So there's now also forget this for a second. There's also the claim now. There's another monodal structure on this one same category of bundle types, which is, I call it the tensor product. It is what the K-theorists would call the external tensor product of the bundles, because on the base space of the bundles, it's actually the Cartesian product as before. So they're the same product on the underlying Cartesian types, but on the fibers, it's different now. Where previously we took fiber-wise externally, as one says, the direct sum. Now we're taking fiber-wise, doubly fiber-wise, the tensor product of these fibers, right? So again, over the point that is labeled WW prime, we get the fiber, which is HW tensored as vector spaces, H prime, W prime. The claim is this tensor product is also closed. Its internal home, now denoted by this lollipop notation, but operated on these bundle types, comes out like so. It's it looks a bit more. It looks a little bit cleaner instead of having the linear maps as element of sets down here. It just has the base maps down in its own base space, and then the fiber over a base map is just the linear space of fiber-wise linear maps that cover this base map. So that's how it comes out. And maybe best, since these formulas may not seem too illuminating, to show one little example of it. Yeah, I can't put this, unfortunately, now maybe on the screen all at once. So let me just show this example, and you just believe it, or you make it an exercise and check it yourself. So with this notation now, my computer is doing something in the background that makes it scroll very slowly. Okay, we'll get there. So just to highlight one thing, so these two in monodal flow structure, this doubly monodal flow structure that we found on the category of bundle types, first of all, knows about the monodal structures on the classical and quantum types separately. Here's the ordinary classical home on the bundle types in the case that they're actually concentrated in the fibers, gives the underlying set of linear maps, whereas if you take the linear internal home of linear types regarded as bundles over the point, you get their linear maps of sets and so forth. So we reproduce classical and quantum separately, the closed structures, but now they begin to talk to each other. And remember, this was, if we come back to my motivation, this is getting in the direction of getting an interaction between classical computing and quantum computing, or classical logic and quantum logic, because now we can also do the following. We can have a map from a classical type to a quantum type, which, previously they didn't live in the same category, but now they do. Namely, the classical type we can understand to be embedded faithfully as the vector bundle, the zero vector bundle over the classical type, whereas the quantum type we understand as a vector bundle over the point. See, they kind of live, as one can nicely see here, in orthogonal, in a way, regions of this category. Nevertheless, there's no non-trivial internal home between them. If you go back to these formulas that I showed, you'll find that this internal home just takes it takes the W quantization of H. It takes the linear span of W with coefficients in H. So it takes well, not quite the linear, but the product, actually, not the co-product. Anyway, for finite types. But anyway, it takes the product, the W and X product of this Hilbert spin. And what's going to be really important and very nice feature of this whole language that we're slowly developing here is, even though it's maybe not visible right now, but it turns out that is also equal to the linear home from kind of the trivial line bundle, if you wish, over W to H. So this indicates, as the notation should make self-evident, that we're looking at the vector bundle over W, all whose fibers, just the tensor unit, which, since we're working with complex vector space, is just the complex numbers. If you plug this into the formulas that are no longer visible, it comes down to the same type. So there's now these mixed homes here from a classical type to a quantum type, either as a classical internal home or as a quantum internal home, and they interact with each other. So let's see. I'll try to scroll. See if this works. So here's some proof of these adjunctions. And this is a pain now that it doesn't scroll anymore. And here's something that I want to discuss later. And the next thing I want to highlight is that this inclusion of classical types and quantum types into this now larger category that merges them, bundle types. These inclusions are categorically well behaved. They're reflective subcategory inclusions, which is hopefully evident from the notation here. So in the middle here, I'm showing how the category of classical types. Remember, this is just highbrow terminology for just the category of sets in my present example. Of course, in general, it need not be, but in this example, it's just the category of sets. It embeds into this category of bundle types by just regarding a set as the zero bundle over it. But we can go back. We can, if we have any type over, so any bundle, we can go get a classical type simply by forgetting its fibers. Just extract the base space. You can easily convince yourself that this is a reflective embedding. So it induces a monad, an endomorphism of the category of bundle types, which is given by take any, the round trip, take any bundle, remember only its underlying base space, and then form the zero bundle over that base space. This is an endofunctor, and since it comes from this adjunction, it comes out to be a monad. And this is going to be important. I don't think I'll dwell much on it, but in describing a quantum programming language and in describing an actual formal language that handles these structures that I'm slowly developing here, we need syntactic machinery to talk about the various qualitative aspects that these types have, and it's an old standard idea that it's structures of monads on categories of types that, if you do functional programming, that give you a nice way in the programming language of capturing such effects by what in computer science would be called computational effects. Anyway, so this is going to be important that this is a monad or a modality, actually, as we're going to say, that kind of characterizes the classical types among all the bundle types. Same story here. Quantum types, remember, was just fancy terminology for a category of vector spaces. We can regard a vector space as a bundle of vector space by putting it as a single fiber of a vector bundle over the point. And that embedding, that functor, also has a left adjoint. This is easy to check and easy to guess. It's just a thing that takes a bundle, remember these over sets, and just forms the direct sum of all their fibers to produce just a plain vector space. So for those who, just as a side remark, who know a bit about homotopy theory and spectra, they will see that this operation, innocent as it may look here, is actually quite a deep operation. If you do this in the homotopy-theoretic semantics of this linear homotopy type theory, the bundles that we're talking about are actually bundles of parameterized spectra. And this operation here that takes the direct sum, this is forming the twisted homology of a given twisted theory over W. So there's some deep stuff going on here, but in the simple example, we just take the fiber-wise direct sum. So since these are monads, I just mentioned this, but let me just flash this very briefly, not going into much detail here. But since we have now characterized the classical and the quantum types in our full category of types by this monadic way, there is a standard procedure for turning that situation into language structures, where you would say, okay, we have some effect in our programming language which has a return and a bind operation, and they correspond to the units and essentially the multiplication operation in that monad. And I'll show another example of a monad, but we'll look more closely maybe for illustrative purposes at what it actually does. So let's scroll ahead if we can to see that there's more structure here. And unfortunately, the scrolling is really slow. Now my computer is doing something in the background. Right, here's just a summary of what we have so far. Maybe it's good to highlight this again. I'm not sure, I'm maybe going slow, but it's maybe good to amplify this. So we have this category of bundle types, linear combined with classical, on which these two modalities, these two monads, act classical and quantum. The maps between them are mixed classical and linear maps. And now this is Albert Moore category notation with the superscript here on the category of classical modals on the algebras over this classicality monad. There's just the classical types. We recover our classical category of sets, as it were, and the quantum modals are the actual linear types. And I've very briefly indicated that this arises in a way that lends itself to to formal language formalization. So there's another monad here. And this is going to show that quite some structure that people have elsewhere postulated and spent quite some time just constructing by hand and analyzing just emerges out of this situation. So let's build another adjunction that we can have here. So this inclusion of classical types. Oh, there's a typo here, a typo. So the inclusion of classical types into all these bundle types is not just a right adjoint, but also a left adjoint. I mentioned this before. This is bireflective embedding. So we have an inclusion like this, a co-reflective embedding. But we also had, by the claim that I just made earlier, that the category of types is actually doubly closed monoidal. We have the internal homojunction for the, and this is interesting, for the classical product and internal hom, but with the quantum tensor unit. So this one here, this both is one. This was, remember, actually the tensor unit for the other tensor product. But we can take, since it's all in the same category now, we can take classical products with it. Anyway, so we have this adjunction. And if you look at what this does, is, previously the inclusion of just classical types into types took a classical type and regarded it as the zero bundle over it. This inclusion now takes, or this is no longer an inclusion, but it's still an adjunction. This adjunction takes a classical type and regards it as the trivial line bundle. All those fibers are the tensor unit over W. And now something interesting happens. If we combine that further, so the adjunction I just showed, let me see if I can put both on the screen here, if anything moves. Maybe the CIA is just inspecting my computer right now. So if we take this adjunction here, which is kind of the trivial line bundle adjunction. If we put this here, this left box here, and then compose it with this quantum Lie reflection that I had on the previous pages, we get something quite interesting. We get an adjunction in combination now between the purely classical types and the purely quantum types. It goes through this category of bundle types, but now you can sort of forget about this intermediate step and regard it just an adjunction between just the classical and quantum types. But it is this category of mixed classical quantum types that kind of generates these adjunctions. I'm not postulating these or anything. These are just built from, and they will actually be formulatable in the linear homotopy type theory. This is an adjunction. Well, okay. It goes between classical types and quantum types. It takes a classical type, if you just unwind what I said, to its linear span, the direct sum of the tensor unit indexed by the classical type. And going reversely, it takes a vector space to, and this is just notation for the underlying set. You see, this was notation, as I mentioned before, for the Hom set, the ordinary Hom set between these vector spaces. So this is just a Hom set from the tensor unit to a vector space, but that's the underlying, this is equivalent to the underlying set of points. So here we kind of linearize or quantize, as it were, a classical type by forming its linear span, and conversely, we classicize, I suppose, a vector space by forming its underlying set. And it's maybe interesting to notice again that in the homotopy-theoretic, just as a side remark for those who know about this, in the homotopy-theoretic interpretation of the linear homotopy type theory, where the classical types are infinity groupoids, these quantum types are spectra. This is actually the stabilization adjunction, which takes a homotopy type to its suspension spectrum, and this takes a spectrum to its omega infinity, to its degree zero space. So this is something, even though we started with, categorical trivialities here, the stabilization adjunction is something that is no longer quite completely trivial. In fact, writing it actually down. Anyway, it's a well-known thing. And but what is maybe what I want to amplify more for the purposes of this talk is that this kind of adjunction is actually something that people in linear logic have long banged their head against, and have there's many articles who postulate such an adjunction. And this starts, of course, with Schreiber himself in his original article of 87 or something, 84, I don't forget, 80s, of linear logic, where he was just working with linear types, what I call quantum types here, and wanted a method to, even though it was working with linear types, wanted a method to have access to classical logic. And his idea was to add a modal operator, this exclamation mark notation is due to Girard, add a modal operator which behaves in this way. So he wrote down some rules which are actually going to be satisfied by this injunction, which somehow say that if you apply the, let's see, do I have this here in the formulas? If you apply exclamation mark, the exponential modality to a linear type, you get something that behaves like it's still a linear type since, it goes round trip here, but it behaves now in some sense as knowing about the actual classical set of the classical type of elements of the linear type. And later people, British School, Benton, Biermann, and others in, I think, the 90s, they, the Pariva, first of all noticed, well, Seeley had a big hand in this. Anyway, they noticed, well, first of all, this exponential modality should be a comonad, which is something that Girard didn't originally say. And then they realized, well, okay, if you have a comonad, you want to realize it, induce it, have it being resolved by an injunction. And then they noticed that the kind of injunction you want is just of this type here. So just without us doing anything, it turns out that this category of bundle types that was so very simple actually kind of in a way resolves an issue that many papers have been written about how you should relate linear and classical types. So this is an injunction, and this is maybe the real point I want to make is since the running claim is that this category of types is described.
I just want to let you know you're about 45 minutes in.
Oh, I see. Okay, thanks. Since these adjoints here are all describable in linear homotopy type theory, and I think you can find them not in this notation, but if you search a bit, you can find these all in Mitchell's thesis. This adjunction is definable in linear homotopy type theory, so we don't have to add it. It's just so linear homotopy type theory is not a linear type theory where you say, okay, let's add an exponential modality. No, it's just a dependent linear type theory, which has sort of the usual dependent type formation. You just want to say, well, if I have a dependent type, I can kind of form dependent, sums, dependent products. And you just do the usual things, but now you do it with these mixed linear classical types. And it turns out what otherwise has to be postulated as an extra modality or modal operator in your system just comes out. And this is going to be the running theme, or would be if I had more time to speak, or if this is the running theme of this project, that we just kind of unwind and say, oh, there's so much structure in this linear homotopy type theory that allows us to express lots of monadic and comonadic operations that otherwise would have to be postulated. And in fact, you see, maybe to amplify this point is that it's non-trivial and the subject of ongoing research to take a given type theory and add modalities to it, modal operators to it. This quickly runs into lots of subtleties, and the punchline of the point here is that, or one point I want to make is that if you just have dependent linear type, then just the standard dependent linear type formation gives rise to a whole host of modalities on your full type category and various subcategories that are all definable in that way. That, yeah, I would have more to say about this. Let's see how far we get. So since I need to come to an end, let me just come to the end of this section here. And yeah, I think I promised to show this one more modality so let me just to indicate, and then I stop, just to indicate that another kind of really neat aspect that shows more clearly how we do make contact to something that you would recognize as quantum computation is the following. Let's consider the following relative version of this quantum Lie modality. Remember, we had this, let's make this larger here. Remember, we had this this modal operator, which has this triangle shape here, which is maybe supposed to remind you of a cat, as in standard quantum notation. But anyway, it was the operator that the modality that encoded the quantum aspect, and it was defined by sending any bundle type to the direct sum of its fibers. So if we precompose this with this operation that takes the classical product with a quantum tensor unit, remember there was the operation that takes classical type to its trivial line bundle over it. Well, then we get this map that takes classical types to the linear span. It's really the same. It is the operation that was just one of the adjoints that I just showed. But in writing it as such now, I want to regard it as what people call a relative monad, a relative modality. And just if you just if one just unwinds standard procedures for producing quantum programming code from such modal operators, one finds that this Q operation, Q for quantum, can be coded as something that has these return and bind operations. And if you unwind using this little exceptional equality that I highlighted a few minutes earlier, you see that this quantization modality has the following very pleasant behavior. It's a thing whose return operations, so that means the trivial effect it produces is as follows. It's the operation that reads in a classical type or term of classical type and spits out the corresponding pure quantum state. So, or the Hilbert space, the vector space that we're mapping to here is just the linear span of W. So it's spanned by vectors that I'm denoting by this cat notation here. And this quantization modality literally has the interpretation of taking classical states to the corresponding quantum states corresponding to them. And if you regard these classical states as being the measurement basis, as quantum theorists would say, of this Hilbert space. And the notation with this Q, or this, of course, the notation with the Q here is designed such as to make this reproduce exactly, and I'll close on that note, reproduce exactly the standard notation for qubits, which is maybe the archetypical example of a type in quantum computation. So when classical computing, you of course are concerned with bits, types of bits, which are really just the sets of two elements. If we feed this into our Q machine here, we get a type of qubits, which if we unwind it, well, it's Q applied to the type of bits, which if we unwind it is the quantum Lie modality applied to the trivial line bundle over the type of bits, which as we unwind it, it's the direct sum of fibers of that bundle. So it's the direct sum indexed by bits over this bundle. So it's just since bits is just two element set, it's just the direct sum of two copies of the tensor unit. But as such, it is exactly spanned by these two singled out vectors labeled by the two basis elements, 0 and 1. And this is, of course, what is used in quantum computation and quantum information theory all the time. And maybe may serve as an indication here of how this linear type theory has a chance of actually knowing something about quantum computation. Of course, this is just scratching the surface, but I'll leave it on that note since I'm guessing I'm out of time. And thanks for your attention.
Thank you, Urs. Thank you very much. Thank you for the fascinating talk. So we have some time for questions now. I just want to first thank Urs for the talk. So we have some time for questions. You can raise your hand in the chat, or you can type your question in the meeting chat as well, and I will send the questions to Urs. So I see that we have a raised hand. David, you have a question? Someone in the room? David?
Yeah. Hi. Thanks for the talk, Urs. Really interesting stuff. What in the semantics of this type theory, what kind of a thing is the big type category supposed to end up being? I thought you said a word or two about that right at the beginning, but I didn't quite catch it. So classical type is some infinity topos, and what is the full?
Oh, that's the bundle types. There was the category of so in the homotopy-theoretic semantics, this is parameterized spectra or parameterized chain complexes. But in this simple model, this was the category of linear bundles, vector bundles, if you wish, over sets for varying spaces. Is that the question? Here.
It was whether there's a class of categories or infinity categories.
Oh yeah, right. Very good. I see. Right. No, exactly. That's a very good question. Exactly. So I briefly touched on this at the beginning. So what makes this work homotopy-theoretically is a little miracle in infinity topos theory, which I think I'm sure it was first noticed actually by Georg Biedermann in 2007. I talked with him just recently about this, where apparently he just made this as a remark to André Joyal while they were sitting the coffee break. And so it's the following observation. Classically, of course, there's a dichotomy between toposes and abelian categories. There's a famous category theory mailing list posted by, who's it, Peter Fried or something? No, I forget, where people talk about if there's any way to reconcile the nice context of topos theory and of abelian category theory, since they seem, or they are in a sense, orthogonal. The only category who is both a topos and an abelian category is the trivial category. And in the course of this discussion, they come up with some axioms that are satisfied by both toposes and the abelian categories. And so this is now, there's a definition of AT categories, but any AT category, it turns out to be the product of a topos with an abelian category. So there's no interesting merging of the classical and the linear regime in ordinary category theory. And now a miracle happens. As you go to infinity category theory, toposes become infinity toposes, and stable and abelian categories become stable infinity categories. And now it turns out you can also do this classically. You can consider the parameterization. You can consider and this is essentially the model I've been describing here. You can consider the Grothendieck construction of, say, abelian category of index sets in an abelian category. So you can look at categories of the free product completions of a given abelian category that kind of mixes the category of sets with this abelian category. So this is an example of this type category. But these are not toposes, and they're not abelian anymore. So in ordinary category theory, they're just not nice enough. What saves the day here is that in infinity category theory, the miracle that happens is the following: the category of parameterized spectra. So if you wish, the Grothendieck construction of infinity module bundles over arbitrary base spaces, that is again an infinity topos. And that is what makes this work here. So in the full category of semantics, this category of type will be what in Lurie's book on high algebra is called a tangent infinity topos. It's an infinity topos whose objects are pairs consisting of an object in an actual, or in some base topos, whose fibers are spectrum objects parameterized over that base. And so in general, if you want this in full generality, then I think the answer is what Joyal called Joyal loci after talking with Biedermann about this. So the interesting thing here is whenever you have a nice enough, an infinity category that is close enough to being a stable infinity category, called a Joyal locus, then the Grothendieck constructions of all its parameterizations over the base topos is again an infinity topos, and that is this category of types. So that, yeah, it's actually quite, I think it's somehow quite remarkable. It's a remarkable fact. It's actually, if you know how to do it, it's not so hard to prove the fact that parameterized spectra are again a topos. It has to do with the fact that spectrification is itself a left exact reflection, and from that you can easily see, since toposes are effectively left exact reflective subcategories, this one can see this statement, and this is I think how Biedermann originally saw it, but I'm trying to highlight this picture I have. But yeah, anyway, whether it's hard to prove or not, it's still a profound fact, and this is what drives the existence of linear homotopy type theory. So that was indicated here. If you can see my cursor, here I indicated for this simplicial group hot model, where I was using, in order to be close to quantum computation, we don't want to look at plane spectra, we want to look at HC module spectra. And HC module spectra, of course, equivalent to chain complexes. So what I'm actually writing here is what we've described in a companion article in more detail. It's kind of the infinity category of parameterized chain complex, what some people call infinity local systems. And that is again an infinity topos. And that is kind of the canonical homotopy model for this linear type theory.
Thank you, Kevin. We have another question in here. Mikhail, you have a question, and also there's a question from Mohammed Barakat. But Mikhail, you can go first.
I have actually two questions, but I would try to be short. First, does bind Q implicitly perform measurement or permits quantum interference? Because it kind of converts the classical information into quantum information. Excuse me, I mean bind and return. So I'm trying to figure out, do we lose the quantum entanglement or not? So does it really?
Did you say something about quantum measurement? We're not using anything. I should highlight that I just stopped talking about this when time was over. This was really just the beginning. In order to, I think, see the full answer to your question, we want to go further. Let me just try to briefly highlight this. I need to try to clean my screen a bit so that I see what I'm doing. So the claim is, maybe just to briefly indicate this, that as we proceed with this analysis of looking what dependent type formation we have, what this means, or what this comes down to, we find other further modalities whose binding return, for instance, does encode quantum measurement and everything that comes with this. So as we proceed, we'll realize that on these quantum types, parameterized over classical base times W and gamma, we still have kind of the expected base change adjoint triple, which if our base type is finite, is ambidextrous. It has the direct sum in both spots. And part of what makes this whole exercise that I'm talking about here so nice is that you just unwind the monads and comonads, which are 4, that are induced by this base change adjoint triple, which I'm calling it by the names they have in standard epistemic modal logic. Then we find 4 more monads and comonads that turn out to know everything about quantum measurement and quantum state preparation and so forth. So this takes a bit longer to explain, but maybe let me just highlight one of the tables that I have here. Yeah, I don't know. Let's see. What should we?
Okay, thank you very much. That will guide my search, and maybe I will come back with another question when I read it in detail. And if another short question is, are these equivalences that you mentioned before all constructive, or are they just equivalences of, mathematical objects?
Say again, which equivalences you mean?
The equivalences on the types that you shown much earlier. Like how does the fiber look in slightly different monads? Or the quantum fiber versus fiber?
Right. Okay. Yeah, maybe not exactly sure which, but the general claim is that everything I've shown, even though I've just described it in standard category theory, but everything I've shown is constructively constructible in linear homotopy type theory. In fact, the things I managed to show, I think you can all find in Mitchell's thesis. If you go to Mitchell-Riley bunched homotopy theory, he will use different terminology, but all the constructions are in there, especially if you go to section 2.4, which discusses this base change between linear types. So yeah, so everything I'm showing is supposedly to exist, well, it does exist constructively in that type theory. And I'm just showing the simple categorical semantics. Yeah. Sorry, not sure if this.
Thank you very much.
Okay, thank you, Mikhail, and thank you, Urs. In the interest of time, I'm going to stop the live stream on YouTube, but I think we have more questions. So if that's okay with you, Urs, I'm going to stop the live stream for YouTube. And okay, so that's, and we have one more question from Mohammed. Would you like to ask your question now?
Yeah, thank you very much. Hello, Urs.
Hey,
thank you very much for the inspiring talk. You mentioned this forgetful functor that takes the vector space and then maps it to its underlying set. But you also mentioned that you're not really looking at the Hermitian structure and more of the stuff, you're just looking at the linear structure. So is there a way where you can enhance this so that the forgetful thing gives you back finite sets, that you don't start with a finite set and then go to the linear case and then come back and then you're immediately infinite if you're working over a field like C?
So let's see, what would you... So one thing I can say is I did not speak about the Hermitian structure, but it is implementable here actually in this draft that you can find on the webpage that you can link to from my abstract. There is a section, quantum probability, that does describe how to get the Hermitian structure on all these types. So that can be expedited. In fact, the homotopy theory is needed for that. But now I didn't quite understand, maybe you're saying something like, oh, once we have Hermitian structure in our spaces, there should be another classical quantum adjunction, what should it assign? You want to take a Hermitian vector space to what its set of what, of basis elements?
Yeah, maybe a distinguished orthonormal basis. Maybe you have something like a Frobenius structure or whatever. So something that you don't immediately lose the finiteness of your construction.
Right. So Yeah, so okay. We certainly, so one thing I just scrolled over and didn't stop is from looking at the monads, the co-monads, especially that one gets from this linear base change, what comes out is exactly the Frobenius monad for quantum measurement that is used in the X calculus. So and that was proposed by Bob Cooke and the Oxford School some years ago. So that is one of the other things besides the Girard exponential modality. But this is one of the other classical, in the sense of standard co-monads that people consider on linear types that just drop out here. Maybe I can try to jump to there. So it turns out this is an easy observation, which maybe has not been fully made before, that Cooke's and et al.'s Frobenius measurement co-monad is just what computer scientists would call the co-reader co-monad, but on linear types. And it comes out by this ambidexterity. It comes out being equivalent to its adjoint monad, so it's Frobenius. So I'm almost there, so I guess I can show it. So it turns out that just by doing base change with dependent linear types and rephrasing that, disregarding the adjoint triple and rephrasing it in terms of the corresponding monads, co-monads, that here it is, that does reproduce the quantum measurement monad as used in the X calculus. And that knows, if you wish, that knows everything about the corresponding bases. So here's the little theorem that I'm talking about. If you take a finite set W and take its linear span, then this QW has a Frobenius algebra structure. That's the Frobenius algebra structure that the Oxford School considers. And it's an easy exercise to work out that the quantum reader and co-reader monad and co-monad that are induced just from base change are actually equivalent to the monadic and co-monadic aspect of this Frobenius monad. They coincide by ambidexterity and form a Frobenius monad, and that's exactly the one. And from this, we get all the quantum measurement discussion that is in the literature, I think.
Wonderful. Thank you very much.
Thank you, Urs. Thank you, Mohammed. I think that's all the questions that I see in the chat. So let us thank Urs again for a really fascinating and very enticing talk. I think there is a lot of material, as you have alluded to, that you did not get to cover in your talk. And I thank you very much for giving us a link to your document, which has more of the details. And so let us thank Urs again for the talk.
Thank you very much.
Okay. Thank you, Urs. I'm going to end the Zoom call now. So thanks everyone for attending the Topos Colloquium today. And again, if you want to catch this talk on YouTube, you can catch the link on our Topos website. Thank you so much.
Hey, Shaway.
Thank you.
Chris, do you have time to meet right now?
I'm sorry, David?
I'm sorry. Thank you, Shaway.
Oh.
If I could. Urs, do you have time to meet right now?
Yes, I do. Yeah.
Okay. I'll maybe just send me a Zoom link of your preferred link.
I don't have a preferred.
Oh, then I'll send you a Jitsi link.
Okay.
Thanks, everyone.
Right.
Okay. Thanks.
Bye-bye.
Bye.